Hello and welcome to Microtrac's free webinar, Hybrid Technology for Complete Metal Powder Morphological Characterization. If you have any questions during the presentation, please type them into the question box in the control panel and we'll be happy to answer your questions at the end of the presentation. A recorded version of this webinar will be available on our website, microtrac.com. Your speaker today is Terry Stauffer. Terry works closely with Microtrac as a particle characterization specialist. He has over 40 years of experience in the industry. In today's presentation, we'll go over metal powder manufacturing processes, the process for manufacturing powder metallurgy parts, the quality control requirements for metal powders, and the instrumentation used to measure quality. And at the end of the presentation, we'll be answering questions. So without further ado, I'll turn it over to Terry.
Thanks, Claudia, and thank all of you out there for joining us today. So let's get started. In metal powders manufacturing, two types of processes are used: direct reduction and atomization, which is the most common. In direct reduction, iron oxides are reduced in the solid state to produce sponge iron, which is then ground into powder and annealed, and then reground. The final powder has a much more irregular shape than the more spherical atomized powders. Atomization includes three types. In gas atomization, a turbulent stream of molten metal forms droplets as it cools in a surrounding gas chamber. In liquid atomization, a stream of metals ejected at high velocity and intersected by a high pressure liquid stream to speed droplet formation. The more rapid cooling allows formation of finer particles than gas atomization, which has a lower limit of about 10 microns. More rapid cooling, they have generally wider distributions than gas atomized powders. There's also centrifugal atomization, where the powder is compacted into a rod, turned into an arc, and rapidly rotated in a spindle, which liquefies and forms droplets that cool and get collected in a chamber. There are a number of powder metallurgy parts manufacturing processes used now. The oldest is pressing and sintering, where the parts first compress by die compaction at room temperature, followed by a sintering at high temperature. The final part has some porosity to it. The lower the porosity of a final powdered metal part, the higher the final strength and hardness. In powder forging, a pressed and sintered part is heated to a high temperature and then hot forged. Hot isostatic pressing, HIP, the powder fills a mold, which is evacuated and heated to high temperatures while it's subjected to external gas pressure up to about 15,000 psi. Electric current assisted sintering is similar to HIP, except the heat is electrical, localized, and massive resistive heat. It can activate other mechanisms like surface oxide removal. Metal ejection molding. This process can produce more complex parts than the previous ones because it's a mixture of the powder with a binder, which gives it fluid properties which can flow into small spaces and passages. Selective laser melting. This is one of the two latest that now produce the most complex and durable parts. A laser beam source melts the powder layer by layer. In direct energy deposition, the laser beam is directed right to the part surface, where it's surrounded by a shroud, injecting the powder into the previous layer of the part. Here's some more information on the selective laser melting process. The laser melting process uses a rotating mirror, which by following a CAD pattern directs a laser beam onto the top powder layer. melting the powder layer on top of the previous layer of the part. All particles not melted onto the part are scraped off while the next layer is loaded. Attempts are made to successfully reuse the unmelted powders for as many cycles as possible before it shows too much wear to meet size and shape criteria. Below is an example of the complexity of a metal part that can be made by laser melting. Parts can be very durable as they're made in one structural piece and they don't require any subassembly. They're also much more customizable on demand. One machine supplied with a number of different CAD programs can be used to make individual custom parts on demand. This saves the large expense of tooling to produce a single part type. In the other additive manufacturing process, directed energy deposition, a direct laser beam is focused on the top part layer and the powder is deposited through a radial shroud surrounding the beam. In this process, there's no recycling of powder required, as the powder is deposited on only the part itself. In selective laser melting, the powder needs to be recovered and recycled. About 90% of a layer of powder doesn't get melted to the existing part on each pass. The excess powder is scraped off as the next layer is being deposited. If the powder isn't recovered, a 1 pound part could end up using 10 pounds of an expensive alloy powder that would be discarded. In order to reuse the unmelted powder, it has to be remeasured to ensure the morphological properties are still within spec. Powder morphology, sizes and shapes, affect important properties of both the powders and of the powdered parts. Flowability, packing density, and level of contaminants for powders, plus green strength, porosity, sintered strength, and final mechanical properties for PM parts are all affected by both sizes and shapes of powders. The powder morphology affects all these properties. Flowability is affected by mainly shape. Jagged-edged and elongated particles interfere with good powder flow. The remainder are all affected by both size distribution and shape. Multimodal size and spherical shape provide higher packing density and therefore higher values for all the remaining properties. The unimodal particle distribution on the left has a larger void volume than the bimodal distribution on the right. Here are the methods used in measuring powder morphological properties, which include both sizes and shapes. For size measurement, laser diffraction has been the dominant technology used for industry in decades. Producers of powders use it in outgoing QC, and their customers use it to verify size specs at incoming QC. And that isn't about to change anytime soon. Laser diffraction is fast, easy, accurate, and robust, and it's widely relied on across all industries. Shapes are being measured by a more recent technology, dynamic image analysis, which reports some 30 different shape and size parameters. This technology has grown rapidly in the last decade for its ability to provide powder characterizations that can't be detected and distinguished by size alone, like how round, oblong, smooth, or rough surface the particle is. These characteristics also can have a great effect on quality. new hybrid instrument, it does both laser diffraction and dynamic image analysis simultaneously, is now available. Here are photos of the instrument, the Microtrac sink, where the liquid dispersion module is shown on the left, the optical bench and electronics in the middle, and the dry powder dispersion module on the right. The dispersion modules, each with its own sample cell and mounted on 4-ball bearings, can be interchanged within 10 seconds. And all tubing and electrical connections are mated automatically. Here's the top-down view of the sink's hardware integration. One bench, one sample, one flow path, one sample cell, one measurement, one user interface, but 2 analyses and 2 complete data sets. Clockwise from the top, the laser diffraction hardware includes the 3 lasers with an option of red at a longer wavelength or blue, a shorter wavelength, for 2 of the lasers for highest accuracies at different ranges, and 2 diode detector arrays on the right measuring scattered light from 0 to 165 degrees. The sample cell, one mounted in each dispersion module, is located where the white arrow points, and the dynamic image analysis hardware includes the high-speed LED strobe at the top and the optics and digital camera assembly in the lower left. This is a comparison plot report available in the laser diffraction software for comparing size distributions of recycled powder streams in an SLM process on one graph. The comparison plot is a way to spot if the recycled stream has become too fine for continued use. A few slides here on the laser diffraction data from the sink. Callout 1 here shows the various tabs for the overall sink software data. Summary data, tabular data, raw data, Setzero calibration data, and the tab for size and shape for access to the image analysis post-measurement software. Below that row, callout 2, is the laser diffraction data in this display view. The list of summary data, percentiles, size percent, peak summary, and below that, the distribution graph. To the right is a list of more features accessible: recall, validate, export, and print data, set up pass-fail tolerances, create trend charts and custom reports, and compliance with 21 CFR Part 11. These views are of the laser diffraction tabular distribution data on the left, the raw data in the middle, and the Setzero display on the right. Tabs in the upper right of the summary data display pull up supplemental measurement information on the left, all the settings for the SOP used, and the security information. This is a set of the parameters that Microtrac reports for the sink image analysis data. Rather than go into each in any detail, I'll describe in 4 general terms what they measure. First, of course, is size. It reports 12 different size measurements of each particle in various diameters, lengths, and more. The last 3 columns are shapes of different natures and are generally expressed as ratios of size parameters on a scale of 0 to 1. Form factors include 10 different parameters that indicate how closely the particle is to being a perfect sphere, or various aspect ratios or elongations of the particle. Surface smoothness parameters are just that, 3 different parameters can indicate the texture of the particle surface. 2 other parameters report the overall light intensity coming through the particle, transparency, and the curvature of the particle as a gradient of light intensity. Interim size parameters are used to calculate a number of shapes. Here, the shapes that can indicate problems with a metal powder sample are shown in red. Width over length aspect ratio, a form factor, solidity, a smoothness factor, and transparency, the intensity of light coming through the particle. The gray outline of a particle image will be used as an example of parameters which can indicate contaminants or off-spec particles in a metal powder sample. Elongated or rough surfaced images can be used to quantify off-spec powder. An elongated particle measured by width over length aspect ratio on a scale of 0 to 1, a low value indicates a more elongated particle. A rough surface texture or fractured particle would have a low solidity. On a scale of 0 to 1, 1 indicates a smooth convex surface. An elongated, rough surface or translucent image can indicate contaminants in a metal powder sample. The translucent image with transparency on a scale of 0 to 1, a high transparency, would indicate a glass or plastic charred or translucent mineral particle. Specification limits on these parameters would be assigned by the QC manager. But don't be overwhelmed. No more than a few parameters are used on any one application. Here we'll use the scatter diagram display in the image analysis software portion of the sync to do a quick evaluation of the values of the parameters of interest to us. The scatter diagram, the blue graph, indicates where every particle in the sample is located with respect to the parameter distributions shown in the red X and Y axis graphs. Darker blue areas are areas of higher concentration. The X-axis graphs shows the area equivalent diameter, the dA, and the Y-axis, the width to length ratio. The dA shows a distribution from 20 microns with a few particles as large as up to 140 microns. As width over length decreases, it indicates the particle being more and more elongated and non-spherical. The Y graph shows the bulk of the powders with a width to length ratio greater than 0.9, very spherical, but there's also a very long tail of particles that goes down to about 0.5, which are particles that can cause quality problems with the PM part. Here we can evaluate the solidity and transparency parameters. Any two parameters, sizes or shapes, can be shown for comparison. The X graph is solidity, the smoothness factor, and it shows extremely smooth particles. Solidity near 1, with only a negligible few below that. The Y graph, transparency, is centered around a very low transparency of 0.25. We can conclude there is no concern about foreign translucent contamination in the sample. So we can focus on width over length to determine the extent of off-spec powder. Identifying off-spec metal powder, width over length ratio on a scale of 0 to 1, lower values indicate more elongated images, as I said, representing powder with non-spherical shape. A sphere would have a width to length ratio of 1. The images here, copied from a small segment of 2 different image files and sorted by width over length ratio in ascending order, with their width to length values displayed are obviously fused individual powder particles which form during cooling from the atomization process on the left. Too many particles like this would be a problem in a powder batch for PM manufacturing. The sample on the left is a fresh batch of powder, and the sample on the right is from a recycle stream. A portion of the low width to length ratio particles has elongated shape, but not quite as distinguishable as fused individual spheres, and from a smaller size fraction than we saw with the fresh powder. So we can identify and quantify the fraction of elongated particles in a sample by the following method. Here's a function in the View Particles display, which can be used for isolating groups of images matching a user search criterion, often searching to isolate and quantify off-spec subpopulations. Selecting the Search Particles box in Callout 1 brings up the particle query window, Callout 2. Here's a search for particles having width to length ratios less than 0.9, which might be the low-end specification a PM part manufacturer has set for his suppliers, because they don't want particles that are too elongated or agglomerated. Any number of limits on different parameters can be added to a search. And any number of searches that include one or more parameters can also be set up for any single measurement. So here we searched for the elongated or agglomerated particular particle population, and the result is shown in callout 4, highlighted in blue. It reports that portion of particles meeting the search criterion is about 22% by volume of the whole sample and has a particle count of about 6,000 out of a total 52,000 particles in the sample, or 12% by number. Examining the image file, we see the particles are beginning to show elongation from a perfect sphere, but the spec limit set depends on the individual application needs. Some PM processes need near spherical or near a W2L value of 1, and others can tolerate limits on a lower W2L ratio. In summary, sizes and shapes of metal powders need to be measured to meet suppliers' and users' QC needs, to identify and quantify contaminant particles for all processes, and to monitor recycle streams in laser melting additive manufacturing. Laser diffraction is a size technology in the industries for size QC, and dynamic image analysis is the technology to use for shape QC. A combination laser diffraction dynamic image analyzer can now be used to make both measurements on the same sample in a matter of minutes. Up to 30 different size and shape parameters are reported, and key powder parameters can be identified and quantified. That ends my presentation, Claudia. I'll turn it back over to you for questions and answers and announcements and a summary.
Thanks, Terry. We're going to begin answering any questions that were submitted. Please feel free to submit any even right now. I will get them right away. And before we get to that, I just want to say thank you to everyone for attending our webinar. We will be providing complimentary lab analysis on your samples, whether it's imaging, laser diffraction, or dynamic light scattering. Feel free to send in a sample by emailing Tony Weigel at microtrac.com, or you can even visit microtrac.com and submit the form on our website for any additional information. So thanks again for joining us, and we'll just wait a couple minutes to see if we get any questions for our webinar. Okay, so our first question is, someone wants to have more information about the solidity measurement.
Okay, the solidity measurement is one of 3 parameters that can indicate how rough the surface texture on a particle is. On a scale of 0 to 1, a solidity of 1 would indicate a particle that has a perfectly smooth convex surface. A particle with a low solidity value would be a very jagged-edged particle with a rough surface. A rough surface particles will not have good flowability. Smooth surface particles will have good flowability, and that's important in a lot of processes, and especially in manufacturing powdered metal parts.
Great, thank you. So our next question is, are you able to perform shape analysis on particles that are smaller than 30 microns?
Yes, we can measure shape characteristics down to 5 microns.
Okay, and what is the benefit of the simultaneous measurement of laser scattering and dynamic imaging when compared to older systems that measure these properties sequentially? Are there correlations that can provide insight with these properties measured simultaneously?
The one big advantage is that it takes a measurement on the same sample at the same time. So both technologies are looking at the exact same sample. They're not looking at a sample split out and made on one device and another sample split out and made on another device, because the 2 samples can differ a bit. Also, getting them done simultaneously saves time, and integrating the 2 technologies into one instrument saves a lot of money, if you've ever looked into this, versus the cost of a complete laser diffraction system and a complete dynamic image analysis system. So it's simplified, it's less expensive, and it's more accurate in measuring the same sample at the same time.
Thank you, Terry. Okay, it looks like we got a couple more questions. In terms of the descriptive shape measurements, how are agglomerated particles, like ones that look like Mickey Mouse ears, differentiated from a single elongated particle with the same width length?
Yeah, good question. The agglomerated particles that look more like Mickey Mouse, that's a good analogy. They can be distinguished very easily by applying one of the surface roughness parameters. An agglomerated particle will have a lower surface smoothness coefficient, like a lower solidity or a lower convexity, and a very smooth, round single particle will have a very high solidity or convexity. So they're very easily separated.
So I guess this person wants to know how long does a typical measurement take, and also when you're measuring size and shape simultaneously, how long does that measurement take?
It's up to the user. We do have an active screen that shows the distribution as you're measuring the sample. And one thing you can do is watch that histogram that's forming as you're measuring it. And once that histogram stabilizes, you know you're measuring a representative sample, and you've measured it enough times that it's no longer changing. Depending on the type of material, and especially on the size distribution that you're measuring, sampling times can vary anywhere from 30 seconds to 3 minutes, maybe, if you have an extremely wide sample distribution. Most measurements are done, 90% of measurements can be done in less than a minute.
Okay, and what is the difference between solidity and sphericity, or circularity?
The solidity is an indicator of the surface roughness of the particle, which is a roughness factor, and the sphericity is a form factor, and it tells you how close the particle is to having the shape of a perfect sphere. Now, you could have a perfectly spherical shape, but it might have a fine, ragged surface structure. The surface structure would give it a lower solidity, but it would still look like a sphere overall.
Okay, and I think there's still some confusion about the how long a typical measurement takes place when using laser diffraction and dynamic imaging. And we have a really great video that shows the process of how the measurement is taken with some animation. So you could see what exactly we mean by simultaneous. But as Terry said, measurements can be done very quickly. Terry, do you want to try to elaborate on that a little bit more?
Well, yeah, I just want to point out that you can see that video, which is an excellent illustration of exactly how it works. It's on our website, and it's right on the landing page, I think, as I recall. The sample is flowing through one sample cell. It's being pumped by one pump through the same circulation stream through the same sample cell, and the laser diffraction technology and the image analysis technology are both looking through the sample cell and measuring their respective parameters simultaneously while that same sample is passing through the sample cell. And like I said, the video will be an excellent illustration of how it all works. The video will also be an excellent illustration of how both the flow dispersion module and the dry dispersion module operate internally.
Yeah, I can include the video in the link to the follow-up email that will have the recording of this webinar as well.
Okay, good.
Yeah, and it looks like we just have one last question. Is there any safeguard against occlusion during measurement?
I'm not sure what exactly is meant by occlusion.
Particles blocking other particles.
Yes, you can. After you do the measurement, you have a complete image file of all the particles, and as you scan down through that image, you can occasionally see where there's a particle overlaying another one, and it depends on the concentration of your sample stream. If you don't see many like that, it's fine, because you're doing measurements of 50,000, 100,000, sometimes 500,000 particles if you want. And if you only have a few that show any multiple image overlap, we advise that as part of your setting up your good laboratory practices is to experiment with different concentrations and get to a concentration where you don't get overlapping images. That's just good laboratory practice.
Thanks for joining us, and have a great day.